بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله. Today is our class on autonomous systems and also about the routing classifications, and we have also the what they call it, the exterior gateway protocol, BGP. So after this class, inshallah, you will be able to define the autonomous systems, and also you will know about the classification of the routing protocols, and also you will be able to describe the basic principle of BGP, and also to identify the BGP attributes. Okay, at first we have to define, and we have to know what is the autonomous system. Actually, the autonomous system simply is a group or a network that's owned by a legal or a single organization. So autonomous system, as we can see here in the slide, is a set of routers that is managed by a single organization and uses the same path selection policy. In other words, it's a set of networks under a unified management. So the main thing here is that we have a group of routers that's owned by a certain organization. Then this group of routers are using the same path selection or the same routing protocol, and also it should be under a unified management. So a unique autonomous system number is actually a number to identify the autonomous system. So it's a unique number, globally is a unique number. It's allocated to each autonomous system for use in BGP routing. So the identification of the system, the autonomous system, is based on this number. So this number is going to be used later for routing purposes and so on. So AS numbers are important because the ASN uniquely identifies each network on the internet. So this autonomous system numbers is something similar to the IP address, but this one is to identify networks or to identify autonomous systems. In the example here, as you can see in the slide, we have two systems or two autonomous system numbers. So the first one here, as you can see, is this. This one is the autonomous system number 65001, and this is the other autonomous system number, which is 65000. So as you can see here, this system is supposed to be owned by a certain organization, and they have to implement the same path selection policy. And also it's supposed to be managed by a unified management at the same time. So this system, the first one on the left and the second one at the right, they can communicate to each other using something called exterior gateway protocol for routing. So the common one that's very well known and commonly used around the world is the BGP. Let us see here. Sorry, let me clean the slide first. Okay. So here, as we can see, we have two systems. Inside this system, we can use the RIB for routing version 1 or version 2, and also we can use OSPF, and also we can use ISIS. But between the two ASs, here, as you can see, we have two different ASs. We have to use the BGP routing protocol. BGP actually stands for Border Gateway Protocol. Okay, ASN number. Each AS is uniquely identified by a number called Autonomous System Number, as I explained, allocated by this organization. So this organization is the legal entity that can give us the ASN or the Autonomous System Numbers for our networks. Until 2007, AS numbers were defined as 16-bit integers, 16-bit integers only, until 2007, which allowed for a maximum of 65,536 autonomous systems or assignments. After this works for a while, but because this number is not enough anymore, after 2007, we have the RFC 4893. This one introduced the 32-bit autonomous system number to increase or to expand the ASN assignments to cover the big or huge number of networks or huge number of autonomous systems around the world. Which the IANA is this one. Internet Assigned Number Authority. IANA has begun to allocate this one, the 32 bits autonomous system number, to regional internet registry, something called RIR, that is allocated in regional locations. So, for example, for Asia, there's one. For Europe, maybe there's one or two. Also for Asia, there's one or two or more. We don't know. This RIR actually is the responsible for the assignments to the local networks. Although this proposed standard has now been replaced by this one, this RFC 6793. Actually, we are not going to go in deep for this because this one is not that much related to our class of today, but at least we want to give you some idea about it and how it works. So the most important thing for the BGP is the ASN or the autonomous system number. The autonomous system number was 16 bits like this. The maximum number was 65,536 networks. Then after that, they expanded to become 32. Then after this expansion, the numbers are written preferably as simple integers. So if we wrote these numbers as a simple integers, they call it AS plane. So this AS plane ranging from 0 to this number. This number is 4,294,967,295. In hexadecimal, it can be like this, as you can see here. Also, then these numbers can be written in what they call it, the AS dot. AS dot will be divided in two parts. The first part is X, and the second part is Y. And between the X and Y, there is a dot here. The X and Y are 16-bit. Every part of this number, actually of this form, is 16-bit. Together will form the 32. For the previous numbers that's assigned based on the previous standard, this one that has only 16 bits here, so the X will be 0, like this, 0. and the Y will reflect the number, maybe number of 6,000, 7,000, something like this, to represent the AS number. So this is only to standardize or to make compatibility between the 16-bit format and the 32-bit format. The number of unique autonomous networks in the routing system of the internet exceeded 5,000 in the 1999, and it exceeds 30,000 in the late 2008, and 35,000 in the mid of 2010, and it exceeds 42,000 in the late 2012, and 54,000 in the mid 2016, and after that 60,000 in the early 2018, and 92,000 as of August 2019. As you can see here, at the beginning, when they create the standard as 16-bit, the number was something around the 5,000. That's why they felt like this 16-bit can cover all needs. But after a while, they realized that this number is no more going to work. That's why they expanded to 32 bits. If you want to see the latest updates about this number of the ASNs, you can go to this website. Then from this website, you can see the latest updates, and you can see what is the maximum number they use up to now. Okay. Now, in this slide, we are going to explain the ranges of ASN, and for every range is for what it's used and so on. This actually, until here, sorry, until here, until this number, oh, sorry, not until this number, until here. This is based on the previous standard. Okay, so here you can see that everything here is 16-bit, and here it becomes 32. So here we have the 0 is reserved based on this reference, RFC 1930 and RFC 7607. Then we can see here from 1 to 2, 3, 4, 5, 5, it's reserved for public use of ASNs. And this number, exact number, 2, 3, 4, 5, 6, is reserved for AS pool transition based on this RFC. And after that, we can see here this range is used also or reserved for public ASN. And this range is reserved for use in documentation and sample code based on this reference. And after that, we can see this range here is reserved for private use based on this RFCs. And this number is reserved, this number here is reserved based on this RFC. Then we can see based on the new RFCs, later after they expanded to become 32, there is another other ranges here. We can see from here, this range is reserved for using documentation and symbol code similar to this. And this one is reserved maybe for research, or I don't know for what it's reserved. There is no information about it. And for this here, we can see the huge number that can be used for public. And this one is for private use. And this one is reserved, maybe based on the RFC here, 7300. So complete table of 16 and 32 bits of ASN is available, as you can see here, all of this. All other ASNs are subject to assignments by IANA. So any number other than these ranges can be used, or actually there's no numbers other than this. I don't know why it's written like this, but anything can be used for public, supposed to be in this range, or this one, or this range. Other than this, we cannot use for public ASNs. So AS numbers, IANA allocates AS numbers to regional internet registries, as I mentioned, RIR. There are 5 RIRs. As you can see here, there's one in Africa, what they call it, African Internet Community, and there is one for Asia Pacific, which is APNIC, and the third one is for America. Then we have another one for Latin America, and the last one is for Europe. So for every continent, there is one RIR. ASN can be obtained from the registry in your region. So if let's say you have, you want to create a network like, for example, UBM campus, or maybe you want to make a network for internet service provider or something like this, then you have to go and get a ASN number to be assigned to your network. Then after that, you have to configure your BGP routing protocol on that edge router. Actually, all of this is I consider myself, I consider it like general information, is nothing to do with it. It's only some general information about the authorities and the ranges and format of the number and so on. We still doesn't know how it works and why we need to use it and how we can use them. Okay, but during these slides, we will understand step by step. Okay, for ASN in Malaysia case study, there's 2 websites. You can go to this website or this website to understand about the numbers used for the autonomous systems in Malaysia. Okay, dynamic routing protocol. Okay, from here, from this slide onward, we are going to understand the concept of dynamic routing protocols and how we can classify the routing, the existing routing protocols based on what, based on functionality, based on approach, based on what exactly. Okay, we will see here how many classifications do we have, and how the things are classified. So routing protocol specifies how routers communicate. As I explained before, even in the class, routing protocol is used to specify how routers can communicate with other routers to disseminate information that enables them to select routes. So the routers need to communicate using routing protocols to exchange the information about the routes in order to allow them or enable them to find the best route or the best path between any 2 nodes in a network. Routing protocols commonly used in the internet. Before this, one more thing I want to remind you about it, which is the thing that we need the routing protocol for. Why we need the routing protocols or dynamic routing protocols? Actually, we need the routing protocols for routers to allow routers communicate, to exchange, as I mentioned just now, to exchange the routing information among the routers to find the best path. But before this, before they can find the best path, they can, based on this routing information that they exchange, they can build the routing table. they can build routing table. So every router can have its own routing table. Then based on that routing table, the router can find what is or where is the best path. Okay. Routing protocols commonly used in the internet. So we have routing information protocol, RIP, and also we have open shortest path first, OSPF, and also we have intermediate system to intermediate system, IS-IS. And the last one, we have border gateway protocol, BGP. Actually, these four are very common, but there is not only this. There is a lot of routing protocols, but this is the common one. Anyway, the RIP actually is used for networks that has small size, because this one maximum path length is 14, if I'm not mistaken, 14 hops. More than 14, it doesn't work. That's why we prefer to use OSPF, and OSPF is commonly used everywhere. OSPF is commonly used everywhere, in every network. For this one, I think this one is already obsolete. And for the BGP is the predominant protocol that's used currently in the internet for the exterior gateway protocol. Okay. Here in this slide, we will see the classifications of dynamic routing protocols. There are many ways to classify routing protocols. So the first classification is based on what they call it intra-autonomous system versus inter-autonomous system. So if we go back to this slide, inside the autonomous system, the same autonomous system, inside the same autonomous system, we use routing protocols that's intra-routing protocols or intra-autonomous system routing protocols. And if we want to communicate or to use routing between more than autonomous system, so in this case, we have to use inter-autonomous system. Inter-autonomous system. So inter means between different autonomous systems, and intra means inside the same autonomous system. So this is the first one. And the second one, so sorry, before that, this one is based on the location inside the autonomous system or outside or between the autonomous systems. This one, actually, this classification is based on the approach of how the routing protocol is working, or based on what metrics they find or they select the best path. So this classification, the second classification, is based on the path selection, based on the way of the path selection. So here we have two types. We have distance vector. Distance vector is like RIP. It works based on the number of hops. So it considers that the larger number of hops means the worst path. So the best path is the one that has less number of hops. And the link state here is one of the link state protocols is the OSPF. OSPF is considering the speed, considering delay, considering bandwidth, many things is considered. And also they have priorities and many things. That's why they call it link state. And the third routing protocol classification is based on the information exchange approach. So if the routing protocols, if they are using Unicast to exchange routing information, they're supposed to be under Unicast routing protocols. And if they use Multicast, they have to be under this class. So each of these classification techniques will be discussed in the following slides. Okay, the first classification is the intra-AS and the inter-AS. The intra-AS is called interior gateway protocols. So the protocols that can be used here inside the autonomous system, actually they are this type, under this type. So intra-AS is exactly the same name of iGP, iGP protocols. This one is eBGP protocols. So the same thing, either to use eGP or to use inter-ASB or to use iGP or intra-AS. It's the same name. So routing protocols can be classified into intra-AS and inter-AS based on their working area. So it's based on where they are working. Is it inside the autonomous system or between the autonomous systems? So as you can see here, this one is intra here, and here is another intra, but this one, the one that's used to connect the two different autonomous systems is considered inter-AS. So here, one of the examples of the interior gateway protocols is the OSPF and also the RIP. Am I right? So RIP and OSPF are both considered as AGP or interior gateway protocols. For the BGP actually is considered exterior gateway protocol or inter-AS. But if we consider the other classification, which is based on the route selection or based on the metrics, RIP actually is what they call it vector-based, and OSPF is link state. So interior gateway protocol can be vector-based, can be link state. Also, the exterior gateway protocol can be what they call it vector-based, and also can be link state protocol. This results in a two-level hierarchy. So as you can see here, we have a hierarchy. This one is low level, and this one also low level. This one is a level up. So why we do this? For what we need to do this? For many things, for many issues, to minimize the traffic, to make different routing policies based on needs and so on. So we are going to explain this later. Routers in the same AS run the same intra-routing protocol. So inside the same autonomous system, we have to run the same routing protocol. So it's not practical to have a mix of routing protocols like RIP, OSPF, and so on together in the same ASB. In the same AS or in the same autonomous system. So it's better to use the same intra-AS routing protocol, unless we have a technical issue. Sometimes we have different devices, manufacturers or something like this, and one is supporting OSPF and the other one is supporting only the RIP, then we have to deal with that case. But that case is not the best. So the best case is to use the same routing protocol inside the same autonomous system. So routers in different AS may run different intra-AS routing protocols. As you can see here, in this autonomous system, we run OSPF, and in this autonomous system, we run RIP, but this is not going to affect anything. Why? Because they have to communicate through another routing protocol, which is the BGP. So it's this protocol is not going to affect the other part. Very important reason to use this hierarchical two-level hierarchy is to minimize the routing table sizes. To minimize the routing table sizes, because if let's say we consider this one as one system, then this router have to have one entry for this router, one entry for this, one entry for this, and one entry for this. So the size is already increased. And also this router has to have entries for this router, and this router. So we will have a big number. In this case, we will have 4 entries in this router. But if let's say we have 1,000 routers, then inside the same router, we will have 1,000 entries in the routing table. That's why they divide the network into 2 parts. If let's say here we have 200 maybe, and here we have 20, the routers inside the same network here will have 20 entries only, and this network can have maximum 200 entries. So we can see that the size is already reduces. Also, we have to consider if let's say we have another network here, another network here, and if let's say this one is 500, this one is 600, maybe this one is 1,000 routers together. If we don't use the 2-level hierarchy, then every router must have entries for all existing routers together. Then the big number will be inserted inside every routing table. Then the routing decision will become very slow. This is the main concept of why we use the 2-level hierarchy. The figure shows here, this figure shows the working area of intra-autonomous system and the inter-autonomous system. As you can see, this bubble here is to cover or to show the area of this router. Where is this router working? And also this area is showing the place of, or the area of this routing protocol. And for the BGP, which is the inter-autonomous system, is going to work only in this area. So it's not going to find paths inside this network like for these routers and so on. So here in this area, we have to have only information about the edge routers, only information about the edge routers. Okay, intra-autonomous system within an autonomous system, for example, within the AS65000. Which is in this example is the RIB version 1 and 2. For the autonomous system 65000, this is a mistake actually. This one is 001. They use the OSPF protocol. So the Intra-AS protocol here is the BGP. Okay, Intra-AS versus inter-autonomous system. We will see here what is the features of every class. So intra-autonomous system, known as interior gateway protocol, also used within an autonomous system. Example of them is the RIB version 1 and 2, also OSPF and ISIS as well. For the inter-autonomous system, known as exterior gateway protocol, EGP, used to control communication of route information between autonomous systems or between different autonomous systems by means of routing policy and route filtering mechanisms. Example of the EGP or the Intra-AS is the BGP. Why we need Intra-AS and Inter-AS routing? The first reason is the scalability. So scalability, as I mentioned, is due to the 2-level hierarchy. So 2-level hierarchical routing saves routing table size and reduces routing traffic. If we don't have this kind of 2-level hierarchy, then every router in the network connected to the internet have to know about every router around the world. So maybe it will have a very huge, very large, big number. So it can be millions of entries or even more. So that will cause the router to spend a lot of time or a very long time to find the best path. That's why the two-level hierarchy increases the scalability, improves the performance of the routers by reducing the routing table size. The other thing is the routing policy. So for the inter-autonomous system, which is between different autonomous systems, network owner, for example, service provider, wants to control over how its traffic is routed and whose traffic to be carried on its network, and use routing policies to filter traffic to the network. So here we have to, for the inter-autonomous system, we have to do filtering, we have to implement some policies to control users and to prevent some users, to allow users, and so on. But for the intra-autonomous system, inside every autonomous system, because in here we have a single administrative domain, the focus is on the routing performance only. So for the inter-autonomous system, they will focus on different things, maybe filtration, security, other purposes. But inside the same autonomous system, we have to focus only on the performance. This is the reasons about the use of inter and intra-autonomous system. So this is the first classification. As you can see here, we have multiple classifications. The first one is already explained. This one we already explained. Now we are going to take the distance vector versus link state. Okay. DV, distance vector, actually is shortened as DV, and link state is shortened as LS. So DV versus LS here, as we can see here, most routing protocols can generally be classified in two classes, like DV and link state. So for DV-based routing protocols like RIP, as I mentioned, and also BGP. So RIP is based on the hop numbers or hop count, and the BGP is based on path vector routing. The third thing is the link state is based on the link state based routing protocols is for example IS-IS or the OSPF. So both of these are considered link state. Why? Because they are considering many metrics like delay, speed, what they call it, type of connectivity like simplex or duplex, full duplex. All of these features of the connection is going to be considered. That's why they call it link state. Then here we have Unicast versus Multicast. Okay, honestly, to tell you is the first and second are mostly important. This one is, this classification is not a big deal actually, but we are going to explain it, and also we have to understand why we classify this way. But honestly, this too is much important than the third one. So here, for the Unicast versus Multicast routing protocols, Unicast is point-to-point. Actually, the Unicast protocols is the protocols that's communicate routers as a point-to-point connectivity. So every router will send to the targeted router by its I don't know how to say that. So they don't use broadcasting. They use unicasting for exchanging routing information. So here Unicast routing protocols compute paths for unicast traffic, provide single or multiple paths for load balancing between each source destination pair. So here they can compute the paths based on the unicast traffic, and also it can provide single or multi paths between each two source and destination. The example of this is the RIB, OSPF, ISIS, and BGP. So all of the common protocols are unicast based. Also, we have multicast, which is point to multi-point. Multicast routing protocols actually computing the paths for multicast traffic typically result in spanning tree. So spanning tree connecting the source to all receivers. So as you can see here, we have something called spanning tree connectivity, which connects every source to the other destinations or other receivers. So that's why they call it multicast based. Why? Because the receivers are considered as multicast members. Examples of this kind of protocols is what they call it PIM-SM, PIM-DM, DVMRP. All names are written here. So that's all about the unicast. Okay, now we came to the main point of our class of today. So the main point of today is the BGP, which is an exterior gateway protocol. Before this, we didn't take any exterior. We only take interior. As you remember, we have taken the OSPF protocol, which can be used inside the autonomous system, inside the same autonomous system. And it's based on link state. And also it considers a lot of metrics to find the best path. For today, we are going to learn about the BGP version 4, which is the predominant protocol that's used worldwide. Okay, BGP version 4 actually is under the RFC 1771. The only inter-domain routing protocol currently in use. All previous versions of BGP are obsolete because before this we have older versions that's already obsolete and not in use anymore. It utilizes a path vector protocol. So BGP is also path vector is something similar to the RIB, which is not considering the link state between routers. It employs the classless interdomain routing. Classless interdomain routing, CIDR. CIDR, I already explained this before in a previous class, but if you forget about it, you have to go and remind yourself, try to search about it and find what's the main concept of it. BGP versus IGP. Okay, BGP is considered as what? It's considered as eBGP, which is exterior gateway protocol. And the IGP is like RIB and OSPF that can be used inside the autonomous system. Okay. Here, as you can see, we have two autonomous systems. The first one uses RIB and the second one uses OSPF. And between them, we have BGP routing protocol is used. So this router and this router, they call it BGP speakers, BGP speakers. Together, these two will form something called BGP peering. So neither AS needs to know or care about the IGP used by the neighboring autonomous systems. BGP propagates routes only between autonomous systems. So this router here will know how to deliver data to this router, but it's not going to know how the inside routers are connected together and what IP addresses they have. It's not their business, you know. So this router should know how to deal with the other BGP speakers in order to provide connectivity among the two different autonomous systems. Okay, BGP operations. In BGP, similar to any protocol, we have a lot of operations. So here we are going to go through them. So BGP runs over a reliable transport protocol. It uses TCP to communicate. TCP uses the port 179 to establish connections. You have to remember these numbers. You have to remember protocols and port numbers for the exams. So it uses TCP. It uses port number 179. BGP speaker is router running BGP protocol. So any router that runs the BGP protocol, they call it BGP speaker. Speakers communicate across TCP, as I mentioned here, to become peers or neighbors. So every two BGP speakers connected together, they call it neighbors or peers. Then here we have external links, which is the connections between BGP speakers in different AS, as you can see here. So this one is external link, and this here is internal links, as you can see. Okay, so internal links, connections between BGP speakers in the same AS. Actually, we can have BGP speakers here inside, for example, this we can have, especially if we have a very huge network that have to be divided in small segments. So in that case, they can use BGP inside the same autonomous system. But in that case, we have two concepts. We have something called eBGP, which is used for this reason here, for outside, for external. And also we have iBGP, which can be used inside the same autonomous system. BGP resolve the connection collisions if two BGP pairs simultaneously try to open connection. Because this protocol is based on the TCP, so one side have to open the connection. If both sides try to open the connection at the same time, then a collision will happen, and the BGP will solve that issue. Here for BGP pairs, from Malaysia case study, we have this website here. You can go through and you can see all of this information. You can find this and so on. This is only for your information. It's nothing to do with. Here for this slide, we have the BGP session establishment. So as I mentioned, one side have to establish the connection. So here is the connection request using the port 179 going to the other side. Then if this side accepted to open the connection, then it have to send what they call it connection response. This one is connection request. This one is connection response. So the connection response will be sent here. So here we will have something called connection configuration. Up to this level, we have the TCP session already established. Then they have to send acknowledgement for the ACK 179 to tell the other side to establish the session. Then after that, here we will start transmitting the data. We start transmitting data maybe from this side or from this side. So both sides can communicate, can exchange data at the same time. Here also after this, we can see the BGP session is established after this 2 steps. Okay. For this actually is what they call it handshake. It's what they call it handshaking, protocol handshaking to establish the session, TCP session, then after that the BGP session. For here we don't have to do anything with it. We have nothing to understand about it, only the way how they communicate. So the first side sends the connection request, the other side replies by sending the connection response over the port 179. So the biggest thing you have to do is to remember this kind of steps for your final, okay, including all of this information. So maybe in the final exam, maybe we ask you to draw this establishment and so on. Origin of routes for BGP. For BGP, actually, we have many types of origins. So let us go back to the slide here. Let me clean first. So suppose that this one is BGP and this one is another BGP speaker. So the origin of routes inside this routing table here, inside the routing table of this router, can come or can be originated from 3 types. The first type is as a static route, which is configured manually to this router. The other type is coming from outside. The third type is coming from inside. Okay. So as we can see here, the first type is the routes learned from other BGP routers. So BGP router only propagates the received routes. Okay. So the first type, the first origin of routes is the routes that's learned from other BGP. Then the static configuration is the routes that's configured manually. So BGP router is configured to advertise some prefixes. Drawback of this is the manual configuration. It requires manual configuration. The advantage is the stability. It's a stable set of advertised prefixes. So it's not going to be automatically changed, maybe disabled or enabled. Why? Because they are static routes. They will be always enabled. But for the dynamic routes, they can be automatically changed. And the other type is the routes that's learned from the interior gateway protocol, like RIB or SPF. So here we can see prefixes received from the iBGP are advertised by the BGP router, usually as an aggregate. Okay, advantage, BGP advertisements follow network state. Prefix is automatically withdrawn by BGP. It's not reachable via IGP. Okay. Okay, now we come to the external BGP and the internal BGP. So external BGP is the one that's used outside among or between multiple what they call it, multiple autonomous systems like this. This is what they call it, exterior gateway protocol. But the one that's used between two BGP speakers, but internally inside the same autonomous system, they call it iBGP. iBGP. So eBGP running between two different autonomous systems. iBGP is running within the same autonomous system. An autonomous system has multiple BGP speakers. So if we have one autonomous system that has multiple BGP speakers, this is what they call it, or maybe they have to implement what they call it iBGP. It distributes routing information among BGP routers. So in this case here, this router is going to be used to exchange data among these two routers, for example, inside the same autonomous system. Also, it minor but important difference with eBGP. Okay, they behave very closely to the eBGP, but they have small differences, which is important. As I mentioned before, the concept of interior gateway protocols inside the same autonomous system is to focus on the performance, but the exterior gateway protocols, they have to focus about policies, about securities, about filterings, and etc. Okay, how BGP works? BGP is like this. Suppose that we have this number here, autonomous system number for this network, which is 100. For this network is 200. For this network is 300. For this network is 400. And here we have 500. So if, let's say, we this network wants to communicate or exchange route information from here to here, then this router will learn about this network here, and after that this router will teach the others about this network. So data will be exchanging among all routers. So here for router 1, it will send its own routes 10.100/16 to router 2, followed by the prefix, which is the autonomous system path, equal to 100, which is the same autonomous system number of the network. Then this router have to add it into the routing table. So inside its routing table here, they have to write the IP address, and also they have to attach the autonomous system path. Then after that, this router is also required to exchange the length paths or routes from other routers to the other neighboring. So the information have to be exchanged, have to be transmitted from router 2 to router 5. So this networks can be sent, I don't know, I think there's some information are wrong here. 10.111. Oh, this example is not correct. So let us take this side. So this router will send information about this to here, and it would be followed by the 100. Then this router, BGP router is the IP address of it is 10. Oh, sorry, this one is also correct. I confused a little bit. Sorry for that. This router will replace this IP address. This IP address, you see, it's the same, as this 10.1.1.1/16, but in the first time it was followed by the 100 here of the original number of the autonomous system. And for this case here, it's followed by 301. So that means this router, if this router wants to send data to the IP address 10.1.1.1, then it have to go through the 300 first, then after that it have to go through the 100. So it's supposed to go this way, and so on. So as you can see here, this side here is 400, 300, and 100. Okay, this is how it works. So the IP address of the network ID actually is going to be sent to the router, followed by the autonomous system number. Okay, in this slide we have something called the BGP header. So when the BGP exchange data, they use packets to exchange that data, and the packets must have data and header. So the header of the BGP includes the 4 fields, as you can see. The first part is the marker. Marker contains an authentication value that the message receiver can predict. So this one is like authentication challenge. So it has a value for authentication. So that value will be predicted by the receiver. Then the second field, before this, the marker actually is 16-bit. Then we have the length, which is 2 bits. Length indicates the total length of the message in bytes. So for example, if the length is 10, that means 10 bytes. Okay, if 100, that means 100 bytes. The third field is the type, which is 1 bit. The type actually is to specify the message type, which have to be one of 4 types. In general, we have 4 types for the BGP messages. So the first type is the open message. The second type is the update message. The third is the notification message. And the fourth and last is the keep alive message. Data, regarding this field here, data actually is variable. The size is unknown because the size can be big or small. It depends on the information they need to exchange. So data here will include or will contain the upper layer information in this optional field. So actually this one is going to go through what they call it encapsulation. So as I explained last time during the lab session, when we travel among the layers, so every layer have to attach its own header. So the previous or the upper layer information, including the upper layer headers, will be dealt with as data. So it will be considered as data. Okay, BGP message types. TCP connection always established through the BGP session. See slide number 22. So if you can go back here, slide 22. In this slide, you can see all of this here, all of this information. Actually, this one is what they call it open, eBGP open, eBGP open, and so on. So it's related to this handshake. So the open message is used to establish the BGP peer relationship, used to establish BGP connection or BGP relationship. The update message is used to exchange route between BGP peers. So after we establish, if let's say we have 2 systems, for example, this and this, the first thing we use the open message to establish the connection. Then we use the update message to send information this way and information this way. After that, we have what they call it notification. Notification is used to terminate BGP connection. If let's say we want to terminate, then we use the notification. Otherwise, if we are still we still need to use this connection, then we have to use the keep alive message, and the keep alive message is to tell the other side that this side is still available. This side is still available. So the keep alive is used to maintain BGP connection. It's sent every 60 seconds. So if the keep alive message is not received after 60 seconds, then the other side is considered dead. Okay, the last thing is the route refresh. Route refresh is used to request the peer to retransmit route if routing policies are changed. So in case of any change at a certain router that requires an update or route refresh at the other side, then the route refresh packet will be transmitted or sent to the other side. Only the BGP devices supporting route refresh can send and respond to route refresh message. So this is a feature. The route refresh is based on the feature that's supported. If the router doesn't support this feature, so it's not going to send or receive this kind of messages. Okay, open message. Establish a peering session. The first message sent after TCP establish. Just go to the handshaking slide and you can see that the open message is the first message sent after TCP establishment, and each peer identify itself to each other. So open message is to let routers identify themselves to the other neighbors. It's used for negotiation. So the open message will include some parameters, some variables. Then the two sides have to negotiate and decide. And after they accept the negotiation, then after that they establish the session. So negotiation could include the version number, some parameters, and so on. Open message is for security, can be used for security, which is optional. The format of the open message, it will include the 1 octet for the version and 2 octet for the autonomous system, for itself autonomous system, and 2 octet for the hold time, and the BGP identifier for octet. And after that, we have 1 octet for the optional parameter, and we have optional parameters. And again, we have another field for optional parameters, which is variable. It can be small or large, depends on the use. Okay, the second type is the update message. It's a primary message used in eBGP. So it's used to advertise or to announce prefix to BGP neighbors. Also, it's used to withdraw a previously advertised message. If let's say, for example, we have these two networks. If let's say this one is 100, this one is 200, the autonomous system, then suppose they establish connection and this one send the information of the 100. Then if let's say there's something happened to change this kind of information, they can use the update message to update the information that's already sent to the router B, for example. And also, if let's say this router A wants to withdraw the information that has been sent to router B, they also can use the update message. It encourages multiple prefixes in a single update. So inside the same message, they can send multiple prefixes or multiple entries, multiple information. The third type is the notification message. It's used when errors happen. So if an error happen at a certain router, they have to notify their neighbors using the notification message. TCP will be closed immediately after notification is sent. So after we send a notification message, the TCP connection will be terminated. It indicates to remote system why BGP was terminated. So when we send the notification message, after we send the notification message, the TCP connection will be sent, but the notification message will tell the other side why we already close the TCP, why we terminate the TCP, what happened. So the other side will know what's wrong with the first side. The last type is the keep alive message. Keep alive message confirms the connection is still active. Rate depends on the hold time. So the rate of the keep alive message is based on the hold timer. The hold timer is negotiated during the open or using the open message and the update message frequency. A common header with no other data is used for the keep alive. So the keep alive message will use the same header, this header, but it's not going to have data. Okay, now we have another thing which is the BGP attributes. BGP attributes, actually the attributes used by BGP to select the best route. So if you remember when we studied the OSPF, we learned about some attributes like cost, preference, and priority, and so on. In here also we have also some attributes for the BGP, but maybe different than the other protocols. So the first attribute that's used for BGP to select the best route is the AS path attribute. AS path attribute. The second one is the origin attribute. If you remember, we have three origins: the static, and routes learned from other BGP, and routes learned from the interior gateway protocols. For the third attribute is the BGP next hop attribute, and also the fourth is the weight attribute, the fifth is the local preference, the sixth is the metric. Okay, so we have 6 attributes. Okay, the first attribute, AS path attribute. It's a list of AS numbers that a route has traversed in order to reach a destination. So if you go here, if you go back to this example, let me clean this slide first to show you what is the AS path. Actually, AS path is this. So the packet comes from here to here. It goes through the AS100 and the AS300. So you can see here 300, 100. So the last is the first. Okay, the order is, as you can see here, the last router we traverse is the first one in the order. So this is what they call it, AS path. For this packet here, we can see 400, 400, 300, 100. That means it comes from here, and before that through this router, and before that through the router 1. This is the AS path. So whenever a route update pass through a new autonomous system, the number of the new autonomous system number is appended. So whenever the packet goes through the BGP router, the ID or the autonomous system number of that router will be appended to the autonomous system path. So AS numbers are listed in order. as I mentioned, in the AS path, the AS numbers will be listed in order as you can see here. So the last is the first. The last router is the first. Okay, that's all about the AS number, AS path attribute. Then number 2 is the origin attribute. It's mandatory. It defines the origin of the path information. As I mentioned, the path origin can be 3, as I mentioned before. It can be configured manually or static. And the second one is learned from BGP routers or BGP neighbors. And it can be learned from Interior Gateway Protocol. So this one, I will reflect the interior origins, and the E will reflect the paths or routes learned from exterior gateway protocols, and the question mark is incomplete, unknown, or via static. Okay. Then number 3, next hop attribute. The next hop IP address used to reach destination. So next hop is, so if let's say next hop is recorded here for this network, it will be the physical IP address of this interface, not the physical IP address, sorry, the IP address of this physical interface. It will be considered here as a next hop. Okay. I think all of this is very clear because we have already studied other routing protocols. For eBGP, always the directly connected neighbors interface. So the next hop for the eBGP is always the directly connected neighbors interface. But for iBGP, which is the BGP that can be used inside the autonomous system, the next hop advertised by eGP should be carried through into iBGP. Okay, so if let's say, let me draw something here. If let's say this one the autonomous system and this one the exterior BGP, and suppose that we have interior BGPs here, so iBGP, and also here iBGP, and this one is exterior BGP. So we already explained where is the next hop of the eBGP. So the next hop of the eBGP is the next physical interface connected directly to this router. For here, the next hop is considered also the next hop that's recorded by the interior gateway protocol, by the exterior BGP. So these two will use the same next hop that's used by the eBGP. The other attribute is the weight. The weight actually is a Cisco implementation. It's assigned locally to indicate a router to choose best exit path. Assigned locally to indicate a router to choose best exit path. It does not propagate through router updates. So this weight is not going to be exchanged among the routers. So higher weight is preferred. That means the higher the weight is the best the path, and default is 0. Default value is 0. Then here we have local preference. Local preference is something similar to the preferences that we have learned for when we study the OSPF. If you remember, we have different preferences depends on the route type. So if the route is static, it may have a certain number. If the route is default gateway, it will have another number. If learned from OSPF, it will have different preferences and so on. So local preference indicates which route is preferred. So based on this local preference, you can find which one is the best path. Also, it's exchanged among routers in the same autonomous system through updates. So this one is used, can be exchanged inside the same autonomous system. So among the BGPs that are located inside the same autonomous system. Higher value is preferred, so the higher the value is the best. Default value is 100. Then we have the metric. Metric is also called multi-exit discriminator. Multi-exit discriminator, exchanged between autonomous systems, but not carried through. So it will be exchanged among the exterior BGPs, but it's not going to be carried through the iBGPs. So low value of a metric is more preferred, and default value is 0. Unless specified, router only compare metrics for paths from the same neighbor autonomous system. So if it's not specified, then the router by default will compare only metrics for paths from the same neighbor autonomous system. It's not going to compare with different autonomous systems. Then here we go to the BGP policies. So BGP provides capability for enforcing various policies. Policies are not part of BGP, and they are provided to BGP as configuration information. Also, BGP enforces policies by choosing paths from multiple alternatives and controlling advertisement to other autonomous systems. So the policies of the BGP is only to choose paths from multiple alternatives and to control advertisements to the other autonomous systems. That's all about the policies. Then we have best path selection, which is the main operation where the routing protocols are responsible for. So every routing protocol is responsible to find the best path based on some criteria. So decision process is based on the preferences. So the best path will be selected as the highest local preference and the shortest autonomous system path, and eBGP over iBGP if the origin, if we have two alternatives for the same, two alternative paths for the same network, one is through eBGP and the other is through the iBGP, so the eBGP is going to be selected. Then the lowest IGP metric, and after that the lowest router ID. So this is the criteria that we have to use when we select the best path. BGP router model, in this diagram here we can see the model and the sequence of operations inside the router. So as you can see here, the router at first receives routes for prefixes from multiple neighbors. So routes can be learned from neighbors and also can be learned as static routes. Then after that, here we will go through the import policy. Router will import the policies. Then after that, some filtration is going to be done here. So filter out unwanted routes. So if there is unwanted routes, maybe duplicates or maybe backup routes, maybe maybe paths which is not good, maybe is going through very long path or something like this. So the unwanted routes will be filtered out, and it will manipulate the attributes of remaining routes. So after we filter the unwanted routes, the existing or the remaining routes will be manipulated based on their attributes to find or to make the decision. Then after we decide exactly one best path will be sent from here to here. So from this box, only one path will be selected. So that path will go through the export policy. The export policy is supposed to do this task. It will manipulate attributes of the best route, influence neighbors' choice, or decide whether to advertise the route to neighbors or not. So this is the last step. After we select the route, then the best path will be used to forward the packet. BGP router model details. Here we can see this one is more detailed. As you can see here, we have the step number 1 is the direct static IGB. So maybe we have multiple direct static IGBs. Also, the second box is the routing policy, exactly similar to the previous model. Then here we have route summarization. So the unwanted routes will be filtered out. Also here from BGP pairs. So the BGP here, it can learn from static, as I mentioned in the previous slide, it can learn from static and also can learn from other BGP peers. Based on this information that comes from static and BGP peers, this box is going to do route summarization or filtration to filter out the unwanted routes. Then after that, based on the criteria, based on the metrics, one route is going to be selected. Then the route is going to be sent to the next box. So the next box is the BGP routing table. Actually, this one is to build the routing table here, to build the routing table for to update, maybe to update. In this case, if let's say we have an existing routing table, then new information comes, then this box will update the existing routing table. Or maybe if we at the first time, then the first information will come from the static and also will be learned from the BGP, then will be inserted inside the routing table. After this, routing table actually is going to be going to be sent to the BGP neighbors, BGP security issues. Actually, BGP has some security issues. The BGP architecture makes it highly vulnerable to human errors and malicious attacks against links between routers, the routers themselves, and management stations that control routers. BGP actually is relies very much on the manual configuration. That's why it's very vulnerable to human errors. So if the humans make some mistakes during the configuration, then everything is going to be affected in a bad manner. Most router implementations of BGP are susceptible to various denial of service attacks. So that means BGP routers are very sensitive to the denial of service attacks. Denial of service attacks is actually is a very common type of attacks. It's well known in the computer network. If you don't have any idea about it, it's better to go and read about it, and at least to build some information, to build some concept about it. Denial of service actually can happen when a certain network device is attacked by what they call it ping flooding. So somebody maybe can create an application that makes a thousands or millions of pings on the same IP address, then that IP address is going to be unreachable, or maybe destination is not responding. This is what they call a denial of service attack. So that can crash the router or severely degrade performance. Many many internet service providers rely on local policy filters to protect their routers against configuration errors, some forms of attacks, but creating and maintaining these filters is difficult, time-consuming, and error-prone. So to solve this issue, we have to have our own local policy filter, which is also very difficult to do, consumes time, and also we can have mistakes when we do it, when we build that local filters. Basic BGP security requirements: for every update it receives, a BGP router should be able to verify that the owner of each prefix authorized the first origin autonomous system to advertise the prefix, and that each subsequent autonomous system in the path has been authorized by preceding autonomous system to advertise a route to the prefix. The requirements, these requirements, if achieved, allows BGP routers to detect and reject unauthorized routes, irrespective of what sort of attack resulted in the bad routes. To summarize this point, actually, they want to say that the BGP, based on this requirements, they can filter, can detect and reject the unauthorized routes, but they don't care about what type of attack is this. They only know how to detect, is it authorized or unauthorized? If authorized, they allow; if unauthorized, they reject. That's all. They don't care about the type of the attack. Conversely, if a security approach fails to achieve this requirement, a BGP router will be vulnerable to attacks that result in misrouting of traffic in some fashion. So the worst thing that can happen when we have this kind of attacks, our data will be routed in wrong, or will be taken to wrong paths, or maybe to wrong destinations. So maybe we will lose the connectivity, or maybe our network will be interrupted, and so on. Okay, security solution requirements. To solve the previous issues, we have security architecture for BGP should not rely on trust among ISPs or subscribers. So BGP shouldn't rely on the trust among internet service provider. So on a global scale, some ISPs will never be trusted. So transitive trust in people or organizations causes mistakes to propagate. The other point, security solutions must accept the same dynamics as the aspects of BGP they protect, and both implementation and architectural security concerns must be addressed. For this reason, they come with something called Secure BGP or SBGP. So Secure BGP is an architectural solution to the BGP security problems described earlier. SBGP represents an extension of BGP protocol. It uses a standard BGP facility to carry additional data about paths in update message. So the SBGP actually is a new extension for the BGP. Also, it helps the BGP to exchange additional data about paths in the or using the update messages. It adds an additional set of checks to the BGP route selection algorithm. SBGP avoids the pitfalls of transitive trust that are common in today's routing infrastructure. How does secure BGP do it? Secure BGP makes use of IB security. So if you remember last time we talked about the IBSec. IBSec when I give you the IB version 6. For the IB version 6, I explained that the security part is already removed from the header. Why? Because they rely on something called IB security, IBSec protocol. So also secure BGP also relies on the IBSec to secure point-to-point connection or communication of BGP control traffic. So every two neighbors, two BGP speakers, they establish connection first, then after that they use IB security tunnel to secure or to avoid any unwanted traffic or unauthorized traffic. They use public key infrastructure to provide an authorization framework representing address space and autonomous system ownership. At stations, digitally signed data to bind authorization information to update message. Also, secure BGP requires routers to generate an attestation when generating an update for other SBGP routers, and also they require to validate attestations associated with each update received from other secure BGP routers. That's all for today, and if you have any questions, I would be happy to reply you, to answer your questions using the WhatsApp group or using the email. You can use whatever way you like. You can contact me anytime using any communication application, and inshallah I'll do my best to answer you as soon as I can. I hope you understand this this topic, and if there is any problem, please let me know, and inshallah we are going to continue for the next class soon, inshallah. Thank you very much.